Hi, very good day to all, and I welcome all of you to the other session of the virtual classes of science here. And in this session, we are going to extend our studies of rotational dynamics, in which we will see the ways to define torque, angular momentum, moment of inertia, and rotational kinetic energy. And we will see the complete relationships between them, and we will have complete ideas on all the concepts. So, welcome all of you again. Let us start with the concepts of torque that we have discussed in the last session of rotation. So, we have already seen that the torque acting on an object can be expressed as, or that is nothing but it is a moment of a force, and we got the relation like tau is equal to cross product of R and F. Let's say for an object which has got a position coordinate, say R, with respect to an origin O, whose mass is say M, on which say a force is acting maybe in this direction, an external force F is acting in this direction. What we can obtain is, see, we know that this is the direction of the force, and we can draw the direction of R as this. A general way of expressing, so that means R and F are making an angle, say theta, in between. So our cross product, the idea of cross product is nothing but it is a rotation of one vector onto the other one. And on this diagram you can say that how the vector R is rotating to F. The vector R is rotating in an anti-clockwise to F. That means R is rotating in this manner. So an anti-clockwise rotation. Direction of the cross product is taken based on what? We can use the concept of rotation of a screw. So if a screw, a right-handed screw, if that is rotating in an anti-clockwise manner, what will happen for the screw? Look at that. If the screw is rotated like this, the screw will gradually come outwards. So we can say that when R is rotating about the F, the direction R is rotating to F, the direction of the torque will be out of the plane of the paper. Or with respect to this one, if this is taken as x-axis, this is taken as y-axis, the torque will be perpendicular to that, or that will be on the z-axis. So I can represent the direction of the z as, this will be the direction of the torque. So from this I can say that the magnitude of the torque will be, the magnitude of the torque is equal to, definitely that is equal to Rf sine theta. And the direction of tau will be definitely, that will be perpendicular to R and F. Or in turn you may say that tau, R, F all are mutually perpendicular to each other. They are mutually perpendicular. So I have got the magnitude of the vector, I have got the direction of the vector. Now you can add one more thing, you can add the SI unit of the vector. Sorry, SI unit of the quantity. What will be the SI unit of the quantity? You know that F has got the unit of m L t raised to minus 2. So if I add another R, that will become SI unit as, SI unit as kilogram meter square per second square. And the dimension formula will be m L square t to the power minus 2. So that's a very simple way to get the expression for the torque. You have got the magnitude, you have got the direction, you have got the SI unit, and you have got the dimensional form. You can see that ml square t raised to minus 2, the dimension is same as that of which are the other quantities you know with the same dimension. You know, work done, energy has got the same unit as this. That will be useful. certain kind of questions related to dimensions. So we have got the expression with the torque, we have got all the mathematics with respect to or based on r vector and f vector. Now let us enter into certain physical concepts related to this. What was your observation with the force F? There is a rotational effect. Actually, when F is acting like this, the body is trying to rotate. Or we will say that it is a turning effect. There is a turning effect for that. Or we can call torque as an analogous quantity of force in the rotational mechanics. So, we have defined torque as a turning effect or an analogous quantity of force in a rotation. And as per Newton's second law, or we will say NLM2, Newton's second law, we define translational force as a rate of change of linear momentum. Rate of change of linear momentum. Here we got a quantity which is also creating a type of motion, not translational motion, a rotational motion. So there is always a possibility for me to represent the torque as a rate of change of, here it is linear momentum, here it has to be what? Angular momentum. Let us see whether this is matching with our expression, whether it suits with that. This can be asked as a question like, what is the relationship between tau and L? It can be a question for you. Or prove that tau is equal to dL by dt. Tau is equal to dL by dt. Let us see whether it matches with that expression or whether we can have this kind of an expression. We have tau is equal to r cross f. R cross f. What is r cross f? We know f is equal to dp divided by dt. I can put it as r cross dp divided by dt. So we got torque is equal to r cross f, which is equal to r cross dp by dt. Let me put it as equation 1. Now let us check product rule in calculus, which is d by dt of r cross p. You know all the parameters. D by dt means rate of change of quantity with respect to time. R cross p, so vector cross product which is inside the bracket. I can express this one as the first parameter into differential of second plus differential of the first cross p. What is p? P is the linear momentum. So linear momentum is nothing but it is mass into velocity. This p is mass into velocity. Here p is mass into velocity. And what is dr by dt? Dr by dt is rate of change of position with respect to time. That is also a velocity. So if I substitute that, my expression, this will change as, this expression will change as d by dt of r cross p is equal to r cross dp by dt plus dr by dt is velocity cross p is mass into velocity. V cross V. What is V cross V? We know that if a cross product is taken with its own vector, V cross V, V and V are making 0 degree with each other, that cross product will be equal to 0. So this is equal to what? R cross dp divided by dt. That will be equation 2. So compare equation 1 and 2. R cross dp by dt r cross dp by dt is equal to d by dt of r cross p. So I can substitute that one over here. So my equation 1 becomes torque tau is equal to r cross f is equal to r cross dp by dt. R cross dp by dt is d by dt of r cross p. That means d by dt of a particular quantity. So that bracket quantity I can call it as what? Equivalent to momentum or analogous to momentum. So the tau is expressed as d by dt of a quantity analogous to momentum. So L is defined as r cross p, or angular momentum is defined as what? Moment of linear momentum. So what is the definition of the torque based on angular momentum? The torque is defined, or that is the actual definition of the torque. What is a torque actually? It's a rate of change of angular momentum. It is a rate of change of angular momentum. So we got Newton's second law in rotational dynamics. So what is torque? Torque is defined as the rate of change of angular momentum. And what is angular momentum? It is the moment of linear momentum. It's a moment of a linear momentum. So we have got the definition of the torque on or based on angular momentum. So the torque can be defined as cross product of R and F, or in physical terms, or as per Newton's second law in rotation, torque is defined as a rate of change of angular momentum. Rate of change of angular momentum, where angular momentum is equal to moment of momentum. Moment of momentum. So that is the way to get the mathematical as well as physical definition of torque, and that is the way to find out the Newton's second law in rotation. Thank you. Thank you very much. I hope all of you must have understood the concept of torque, angular momentum, and Newton's second law of motion in rotational dynamics.